Hello and welcome back to ST118 Statistics and Applications Session 4. In this video, we are focusing on a more specific type of test, and that's called the two population means test. So let's write that down. Two population means test. Hypothesis test, that is. It also comes with different names. Sometimes it's called two sample test because we need to take one sample from one population, so resulting in two sample sets being measured. But sticking to our convention of the goal-oriented naming, so our goal is to examine two population means, right? In other words, we have two populations, distinct populations. Of course, this is mathematical population, statistics population, meaning a set of numbers. And these two numbers can be measurements from the same physical entity in, let's say, two different scenarios, being exposed to two different environments, or else before and after, right? Before certain things was applied, after certain things were applied. Earlier on in time, after some time later. How did this group of things, can be objects, products, people, right? Companies, stocks, whatever it is, numbers, how did this group of things measure, right, after some time? So and therefore there's a population before, there's a population after. There's a population A, there's a population B, so uh, resulting into population means that we want to certainly talk about application areas, because oftentimes, right, whether textbooks or YouTube videos will go through the details of all the calculations, and then after that, the audience or readers like yourselves might just lose track of. So how do I use them? Right? So I want to talk about that to tinkle your mind into associating this skill that you learn or will learn automatically, hopefully, right? So whenever you next see this kind of situations, you will uh, want to use this family of tests. And then we want to discuss specific calculations pertaining to two population means test, and see some examples. Okay, all right. So two population means test. Like I said, it involves two population means, right? So mu1 and mu2. Sometimes textbooks or exercise solutions might just say mu A, mu B, and then changing to another exercise, the answer might look like mu X, mu Y, mu before, mu after. Now, while these namings, they look attractive, right? Very contextualized, is sometimes a little bit also confusing when it comes to writing the hypothesis statements. But so perhaps it is good to just stick to mu1 and mu2, and then say mu1 represents the before, mu2 represents the after, because one is smaller than two. So try not to confuse yourself by frequently renaming that. Let mu2 be the before population mean, mu1 be the after population. Now, I've been using before after, but don't get me wrong, it doesn't mean that there must be time involved. Like I said, it can be two different situations, right? Group A is exposed to the sun and rain. Group B is in the shades, right? Simultaneously, okay? And so we want to compare whose skin is darker on average after 10 hours or whatever it is, right? So you understand that it doesn't have to be having a time gap. So all these situations will begin to fall into what I'm categorizing as the application areas, right? So application areas, and it's good to put them in the foreground, right? So very clearly, we are trying to compare, right? Compare. We are trying to compare usually two groups of measurements, two two populations. So it's like which group, right? Which group is better? Just comparing, right? So you want to get a feel of just compare, just for the sake of comparing, which group or which set, right, or which collection of entities is better than the other. So we have, for example, uh, Group A, the financial stocks. Group B, the utility stocks. Okay, so and as you probably can guess, even if you are not investing, you know that financial stocks, the number of financial stocks in a particular stock market need not be the same as the number of utility stocks in the same stock market exchange. So 10 banking stocks and 4 utility stocks, right? So, but then which group of stocks gives better returns? Now, of course, we're not going to add up the ROI from 10 banking stocks compared with ROI from 4 utility stocks, right? We are going to compare perhaps the average. And there you go. We have the ROIs for the 10 banking stocks. We have the ROIs for the 4 utility stocks under a bigger population of all banking stocks. Many of them. Okay, of course, uh, in real life there won't be infinite number of banking stocks, but it might be hundreds or thousands of banking stocks worldwide or whatever it is, right? Or yet to be listed, that kind of meaning, so that the 10 banking stocks that we can see, that we can measure, become our sample size. All right. And so we want to compare. Our purpose is to compare. Maybe we haven't decided to invest. We just want to compare and write a report and write a blog or post a LinkedIn article and say, hey, I've done this comparison and this is what I found. But, you know, if you say, I think, looking at the numbers, I feel that banking stocks are giving better ROI, you might just get cold eyes because that's how you feel and think, right? It's very subjective. But if you say you have done applied, two population means test, from what I've learned, right? And the result is to reject the null hypothesis that banking stocks are not better than utility stocks. Okay, so so you can then get a more data supported conclusion. So if your goal is to compare two populations, and I'm stopping at 2 and not 1, not 3, because for 1, then we got to go back to the one population being test, right? For 3 or more, we will have to look at the next video to use another technique. And for now, I would just say having the name of ANOVA, right? So use that to do the comparison. Of course, we also can qualify a little bit, right? The two populations. The two populations can be in complex scenarios. Complex scenarios. And of course, this is not saying much, so let me explain. And just after I write down this, time lapsed, the before after situation as I mentioned. Okay. So complex scenario could be that it is simultaneous or relatively speaking happening almost at the same time. So for example, if you're conducting an experiment that maybe it's a medical trial to test a new drug, right? And you want to not measure the new drug based on a standard reference level. So there's no number to speak of, right? So you're going to compare the two populations under complex scenarios, under time-lapse scenarios. For the complex scenarios, if you're doing medical drugs, you have two groups of patients, right? They are undergoing randomly, right? Being given some new drugs, some what we call placebo drugs. That means they're told they're given new drug, but actually it is vitamin C or some vitamins, right? Some non-helpful drug, okay, to these volunteering, consenting, I don't know, cancer patients or whatnot. So you're trying to test this new drug to see if it is effective or efficient in, combating the cancer or maybe even curing the cancer. Okay, so the test will run as planned for 1 month or maybe 3 months, doesn't matter. This 1 month or 3 months, the two groups of patients are undergoing that simultaneously. So there's no time lapse, right? But it is a complex scenario. Why? Because in these circumstances, number one, the new drug might not be administered to the same number of patients as the placebo. That means your blood, not blood, the new drug supply may be a little bit limited, right? So that if you have, let's say, 20 consenting volunteering patients, 5 might be given new drugs, okay, or just because of the limited dosage, right? Not because of intentional. So that in other words, the sample size for the population of cancer patients given the actual drug is 5, and so the sample size for the other population is 50. Just because of circumstances, right? But that's not the complicated part. The complicated part is almost always, as you can imagine, each patient will have very different, medical history, personal living habits, right? Eating habits and all that. So the body immunity situation, whatever it is, medically they are very different. So that it will be quite challenging, right? To sort of compare the population mean effectiveness with a particular reference number. So if this particular cancer, let's just give an example to illustrate what I'm trying to say. If this particular cancer, for this kind of patients who potentially will benefit from this new drug, are essentially seniors. Okay, so in that case, seniors will have led very different lives before they come to this stage, right? And so it will be complicated. It will be complex, right? So that the comparison is not so straightforward. And then we choose a measure. We choose to measure, for example, the number of cells per milliliter or per 10 droplets of blood, the number of cancer cells still found after the end of the experiment. Something like that, something medically meaningful and interesting to quantify the effectiveness of the new drug, right? So that's the complex scenario, right? Maybe it is simple scenario. Maybe it is just simple comparisons of the performances of this engine produced in the Japanese factory and the same company, same model, same engine, but then produced in Brazil. Okay, maybe the company is interested to, maybe the company Toyota, right, is interested to test if the population mean performance of these two sets of engines, to layman customers, they are the same Toyota engine, right? Very, very efficient, powerful, and all that stuff, quality made. But to Toyota, they want to micro inspect into the performance. Are there any material difference, right, before they sell it out to the market as a branded Toyota engine, right? So they want to test, and that will give rise to again, not necessarily complex scenario, but simple comparison, right? Without having to know the engine performance exactly, they just want to compare. So it's not like they hypothesis test the first population. Oh, it passes our quality requirement of 99 marks out of 100. This also passes 99 marks out of 100 because they have to pass quality inspection performance test first, right? That is the one population test. That means they individually test themselves. Right? Now Toyota headquarters want to compare them. So they are all qualified, but then they are still, there may still be relative differences between them, right? So that's the scenario that we want to compare two populations, and importantly, without knowing the means. I don't need to know the values of the population means. Just compare and let the test tell me which one wins. So that brings us to the next point, which is to judge, right? And do decision making. So judging is to decide on win lose, literally. Judge two parties. So literally win and losing, winning and losing, right? So who wins, who loses? What win, what loses? Which one wins, which one loses? So you have two things, two groups, right? Two competitors, two sets of suppliers, right? And they are going to they will compete, right? They will deliver the agreed upon measure. That's the number we are going to measure. For example, it can be daily sales. Okay, so okay, I've narrowed down out of 20 job applicants for this car sales job position. I've narrowed down to two looking like equally good, equally promising candidates. Right. So I don't know who to choose. Okay, today we have invited both of you here to sign this competition job competition agreement, so that within the next 10 days the one who sells more wins. So who can deliver more sales? So sales will be the measure that we use to decide who wins, who loses, right? So that's the situation that might give rise to the need for a two population means test. Or maybe it's not job candidate. It could be two employees, two sales employees. There's now a vacant sales manager position. So who should be promoted, right? Okay, so based on past performances, so randomly pick, right, and then we can decide. Of course, someone might say, my maximum sales was 3 cars a day. Well, my maximum was 2, but I always sell 2, right? More consistent. But then this one is occasional, one time 3-car sales, like very outstanding, right? Or maybe a 5-car sales, very outstanding. But the rest, sometimes 0 sales, 1, 0, 0, so that it averages down. But then, of course, if I'm vying for the sales manager promotion, I want to point at the 5-car sales, my brilliant performance that really trumps the other person, right? Who is just selling 2 cars, no more than 2 cars, 2, 1, 2, 2, 2, 1, 1, 2, 1, 1, 1. So that averages to maybe 1.8, 1. So who wins? We need to then use this tool to help us statistically decide. And of course, there's another scenario which is also compare and judge and decision making, but it's also frequently known as the A/B testing scenario. Okay, A/B testing usually is that we have two complicated designs, right? So when I say complicated, it just means statistically complicated. It doesn't mean the design itself is complicated. It means that we have put in a lot of thoughts. Maybe the outcome is very simple, right? So we put in a lot of thoughts and we are not sure which is good. So A or B, So I'll give you an example in a while. But A/B testing, we have usually, for example, two designs, right? And the question is which one to use? Which one should we use? Right? Oftentimes you are faced with this situation. For example, quick one, right? A/B testing. Those of you who are in marketing campaign, should we use green color or red color? Let's say it's shortlisted down to red color or green color, right? Red color is a very auspicious color in certain culture. Green color is a much more, how to put it, celebrated color, right? More acceptable color in another culture, right? So, which one should we use? And so on and so forth. So, that's one. But the example I wanted to give is in another kind of scenario, like product development. Should we do this or that? Okay. More specifically, let's say we're designing an e-commerce site, yeah, whether it's for ourselves or for customer, like we are a web integration firm, right? Or you are a business, IT business consulting firm, right? You're trying to design a website for a customer. So should we use left? Should we put the checkout icon on the left side of the screen or right side of the screen? Now you might think this is trivial, just whack, right? No, because you want to make sure this screen design is very, very usable, very smooth, very friction free. Because other than having lots and lots of products for sale and discounts and various marketing and selling tactics, you also want a very smooth screen design, something that attracts users. So let's say we narrow down to this question. Of course, there are many questions and therefore many two population hypothesis tests. But this question, should we put the checkout icon on the, it's going to be at the top, but is it on the left side or right side? Now, even for mobile phone these days, the screen is getting very dense in pixels. So it's not a trivial question, right? They're like almost like 2,000 pixels on the longer side of the screen, even for mobile screen. Much less to talk about larger screen. But let's just say our main question is, should the checkout button be on the left or right? Now, in case someone says, isn't that simple? Just put it on the right side, because most people, okay, let's say 60% people, or maybe higher, but let's say 60% of people are right-handed. So of course it's on the right side, right? That's certainly an argument and not wrong, although it is a claim. Remember, a claim is without data proof. What if there is some, sort of unrecorded, but then generally colleagues know it's true, some evidence suggesting that people who come to our websites, right, they are a mixture of both. In other words, left-handers also come in very frequently. I don't know. Maybe there's some suggestion about that. Or some hearsay, right, unconfirmed hearsay that says left-handed people tend to spend more online. Okay, maybe it's done by a university researcher. Okay, does that apply to our website? We don't know, but then it does seem that they have shown it to be true, right? So what should we do about it? So should it be on the left or right? We don't know. So let's do A/B testing. This is the exactly the case. Two complex designs, right? So is it on the left side of the screen or right side of the screen? It's not a complex question. But putting it on the left or right, the thoughts that went in is pretty complicated, right? It's pretty extensive and pretty hard to summarize. So the choice of A or B, left side or right side, we don't know what to do. Which one should we use? That's when we will start to say, okay, the population of daily revenue, right? Daily revenues, should the checkout button be on the left side? Is one population. The daily revenues For the case where checkout button is on the right side, that's another population. So, well, web designers all know, right? They can do it rather easily. Transactions with odd number occurring at the odd number of times. Let's say there are 100,000 transactions for this very, very busy and successful e-commerce site, right? So 100,000 a day. So it will be labeled 1, 2, 3, right? So all the odd number transactions will be given a left-hand side checkout icon, the even numbers, the right-hand side checkout icon, right? So at the end of the day, you can tally. And let's run this for 30 days, 60 days, and then we can use those as the random samples. Right? So that's another case where where the population will be, if we fix this to be permanent, right? Fix the icon to be on the left or on the right to be permanent, then there'll be the actual population of daily revenues. So which one has a higher daily average? Simple, right? Then that will drive the decision to have the checkout icon. Now, of course, you and I can almost already agree that it should be on the right side. I would like it to be on the right side, but who knows, right? Who knows? Maybe this e-commerce site has one section that attracts, hey, left-handers, come here, right? You guys have always been unfairly treated, so come here and buy stuff that fits your left-hand side, personal preference and usage purposes. We have a left-hander mouse and all that stuff. So who knows, right? So we never know. We have to always take the attitude, the humble attitude that I don't know, right? Because when you're doing statistics, especially when doing sampling and all these, we're not asking you to be the wise guy who knows everything. We are asking you to be the statistician, right? The data gatherer who will touch reality, measure reality, and then analyze it. Okay, so from what I can offer you will be these categories of situations, whether it's life or business or personal situations. So all these are without knowing them. So without references, right? Without hard clearance levels, like the score must be at least 60%. We are not interested. We just want to know who has higher marks. That's all. Even if both fail, still who has higher marks, right? So that's the kind of situation we're in. So in A/B testing, we're not talking about pass fail. We're not talking about which one is achieving, record sales higher than 80,000 per day, higher than 1 million per day or whatever it is. We're not having a hard number again. We're just interested in left side is better or right side is better. So again, these are the situations. Okay, so that's the kind of scenarios that we should have this spider sense tinkling and say, hey, look, we are trying to decide, or we have narrowed down to these two items in our short list of possible actions or reactions to competitors' price cuts, right? Price challenges, price battles. So which one should we choose? Okay, so these are the decision-making times, and it will be those situations where we should really think about using two population mean tests. Okay, let's get down to a little bit of more specific discussion on two population mean tests. So for two population, I'm just quite trying to squeeze in a little bit more words here. So for two population means tests, our goal is to decide which is higher, which the relative strengths, right? So the goal is mu1 greater than mu2, mu1 less than mu2, or mu1 equal to mu2. Okay, so that's the goal for two population means test. Mean or means, I'm always not very sure. Two population mean test. Okay, so but let's just say means test. Okay. So under this, we have what is called a PET test and unpaired test. So we have PET. So you decide. You first have to decide, right? If you are the problem solver, you have to start thinking, is this problem involving PET tests, or should I use the unpaired test uh, set of tools and formulas and calculations? So they are very different. Even writing the hypothesis is different. Um, for PET test, right? Let's write them down. The hypothesis. For PET test, the hypothesis will look something like this. Mu d, right? We are trying to decide on mu d, right? So mu d is the population mean of differences. Where each of the di, right, is the xi of population 2 minus the corresponding xi of population 1. So we define it this way. I use 2 minus 1 because it's just easier mentally speaking. Because 2 minus 1 is still positive, right? I would rather not deal with negative number. Having said that, of course, you have the liberty to say, I define mu di to be xi comma 1 minus the corresponding ith item of population 2. But let's just stick with my convention, right? So the important thing, however, here is the I and the I here. They are the ith row, if I can just use that analogy, of the Excel spreadsheet, or for R and Python, the data frame, that's similarly the ith row. So the difference at the ith row is the result of subtracting the ith row ith sample from the second population minus the ith sample from the first population. So at the data level. So you keep doing that, right? And then plus those pairs from the population 1 and 2 that we haven't sampled, but you know, theoretically think of it as you also have done those subtractions, that forms the population, from which the actually measured xi's from populations 1 and 2 will form the di's that we are doing, right? So that would give rise to H naught example only, right? Because we haven't really defined differences of what. So H naught would be mu of d. Let me just use one-sided formulation, but you already understood that this could be the other way around, less than, and then you change, and then it can also be two-tailed, right? The important thing is it looks like one population means test. Precisely. Precisely. And from here on, it's just like one population means test, and we will just use the one population t-test. So t test statistic and everything else follows from that. That's it. Of course, that's the calculation part. What do you mean by paired versus unpaired? What do you mean by unpaired, right? So let me just also write out a sample hypothesis, right, for the unpaired situation. So unpaired situation, we now have mu1 and mu2, right? They still exist, but we kind of ignore them and calculate our own, or invent or create our own difference population. All right, the D is created from the xi's, right, from population 1 and 2. So we didn't ignore population 1 and 2. We still have to sample from population 1 and population 2, but we'll compute it like this. So we create a different virtual world and we enter into that realm, and then compute, right? Reject null hypothesis and conclude that, let's say, mu d is greater than 0. So what does that mean? That the entire population's average, which is result of 2 minus 1, is going to be positive, which means mu2 is going to be larger than mu1. That's the final deduction, right? So we will then first conclude that mu d is greater than 0 at 5% significance level, but at the same time, we want to respond to the original intention, right? So, which is to say that population mean of 2 is indeed larger than population mean of 1. Okay, so that's at 5% significance. But let me just write down the other side, right? So we have mu1 and mu2. And what we're going to do is to write down, for example, h naught mu mu2 minus mu1 h1 mu2 minus mu1 is let's just follow the same, greater than 0, less than equal to 0. And I don't need to waste the rest of the bandwidth here to repeat the fact that it could also be less than 0 and greater equal to 0 and so on. But what I do want to elaborate a little bit more on is to refer you back to the goal here, right? Remember, our goal is to compare, right? So that we can make appropriate action, reaction decisions. Our goal is to know whether mu2 is indeed greater than mu1. So in this case, why didn't we write it like this? Some students will write it this way. In fact, some books will also write it this way, which is not incorrect. Mathematically, this is the same as this, isn't it? Yeah, because if you bring it over, then 0 appears. The important thing in writing your hypothesis this way, I would even insist, is that it brings out the 0 here, right? It brings out the 0. It also standardizes all these writings. Okay, you see that we could have written alternatively h1, right? If you bring these over, right, we will get mu1 minus mu2, right, over there is less than 0. And therefore, our h naught must be mu1 minus mu2 is greater or equal to 0. So if you write it this way, even for the same claim that we suspect the population mean of 2 is larger than 1, we suspect. So mean of 2 minus mean of 1 must be still positive, isn't it? If that's the claim, we suspect population mean of 2 is greater than mean. If that's the claim, this way is clearer because just like what I just said, you are suspecting mu2 is larger than mu1. So mu2 minus mu1 must have some positive left over. This way is mathematically the same, but mentally very destructive, huh? Because mu2 minus mu1, one will have to think, oh, you will then get a negative value because, okay, I see now, right? If mu1 is 1, then mu2 better be 1 and larger, okay, something like that. So it slows down the thinking. It makes our visual mental assessment a lot clumsier. We're not so ready to agree, right? Whereas this is very easy, I think, for most people to see. Oh, you are suspecting population 2 is better than population 1, is it? Performance is better? Okay, all right, I can agree. Claim goes to H1, yes. So you can check rather easily. So I would highly encourage you to write this way rather than fiddle around or insisting on negative values. That's benefit number 1 in writing this over this, the second claim here. Benefit number 2 is much more visible and important, and that is the appearance of the 0, right? So we are suspecting that mu2 is better than mu1. But our claim can also be that I suspect, right? I suspect that mu2 is better than mu1 by at least 3 units. By at least 3 units. If you say that way, right, then you note that this 0 can become plus 3. All right, so to give the notion of by at least 3 units in the claim. So the claim need not just say better, but can be better by, you know what, I dare to say it is better by than the mean of 2 is better than mean of 1 by at least 3 units. So so this 3 can enter here, but it will look very clumsy if you put inside. So how do we put it? Mu2 is greater than mu1 plus 3. Right? So mu1 plus 3 is less than mu2. That kind of writing is not wrong mathematically, but just less obvious. And also here, right, the 0 doesn't come out, so we would have to mentally compute a hypothesized mean to be okay, I think it's 0. So why make it so ambiguous and hard to convince people, right? When your presentation here in the calculation steps is to show people I have nothing to hide. It's very clear. Right? Okay, so try to stick to this. And I won't copy and modify for the rest of the versions like less than and all that. Huh? Okay, so you can try that out as an exercise. So just be careful. Now, but what is very clear is that when you approach a 2 population means test, you got to decide, because right at the start, the writing of the formulation of the hypothesis themselves is already looking very different. Okay, now I kind of jumped ahead to write down the hypothesis for unpaired test before I even discuss what is paired, right, and unpaired. More to show you that there's a drastic difference even when you write down the hypothesis. If you write down the hypothesis with different structure, you can expect the sampling distribution to also be constructed in a slightly different way. The first way, without even knowing paired and unpaired, what's the difference, but by just looking at the hypothesis, and if you have studied well the previous videos, you know that this is just one population means test. So we'll stick to using T. So it's one population T test, and we can just continue from there, right? Obtain the sample size, X bar, S, calculate the degree of freedom, calculate p-value, and we can go. So you can look at the one population means test video to do the rest of the calculations. I want to talk about first what is paired and unpaired, why and when do we use them, and then I want to also perhaps quickly draw some diagrams for you to understand how come we can reduce the paired and unpaired down the paired populations, 2 populations, right? But if it's under the so-called pairing scheme, then we are down to 1 population of differences. What is going on there, right? Okay, so first thing first is paired and unpaired. Imagine that, I'm just going to illustrate. Imagine that we have this need to decide or determine the claim that elder sibling, the other way around, younger sibling performs better than elder sibling. So if you have 3 children, 4 children, then the younger sibling performs better than the older sibling in the university. Okay, so let's say that's the research, right? The hypothesis, the claim without proof, the investigation direction. Okay, then what happens? If you walk through with me, think through with me, we will start having to identify, right, our population. Our population is not all students in the university. Our population will be only siblings who have gone through university. Okay, and in order to not have generation gap, because some siblings are 10 years apart, 15 years apart, right? Number one, the siblings must come from the same parents, right? Number two, they must be simultaneously studying in the same university so that the rules, regulations, the passing criteria, the choice of electives, the core, whatever it is, are more or less similar. Fine. Sometimes, during the transition from one year to another, there may be some changes, but shouldn't be that significant. So that means the two siblings, young and old, must be simultaneously studying. So likely year one, year two, or year one, year three, or year one, year four, year two, year four, that kind of combination. So it becomes a lot lesser now, right? The potential samples, and then we got to find them, have their consent, and maybe agree on the remuneration and whatever, right? So it's like a participation fee, and then start measuring them, or ask them to submit their transcript. Right? So whatever it is, we can use GPA, we can use whatever it is to measure. That's not the point of discussion. So we we perform all the steps, right? Now, whether you reject or not reject eventually, that means whether your conclusion is yes, a younger sibling does perform better, or whatever it is, do not reject or reject. That the younger sibling doesn't necessarily perform better. Okay, whichever conclusion you reach, there will be skeptics. Correct or not? Yeah. So there'll be skeptics who will doubt and say that, wait, your result may not be reliable. Then you say, no, but my sample size is, I managed to find 40 pairs of siblings, right? But your result is still not reliable. How come? Well, because some siblings, right, they are richer. Some siblings, they are poorer, right? So if you do this way, which is to average out the elder siblings, means some elder siblings come from rich family, some elder siblings come from poorer family, or needy family. With the younger siblings, right, and so on and so forth, then it will not be meaningful to average them out, because the richer siblings is not just being rich, but they can afford more learning opportunities, better tuition class, more assessments, more practices, more whatever it is, right? And that can have material difference. So this is bringing up the challenge to the validity of the result. Again, let me stress, the result doesn't have to be showing true that the younger sibling is performing better, or false. Younger sibling does not need to perform better. It's either way, it can be doubted. Okay, either way it can be doubted if you perform it this way. Because averaging up performances of elder siblings from rich, poor, medium families and all that, or families with teachers, right? Families whose parents are professors might get unnecessary advantage, right? Yeah, so whereas the rest don't have this, not not that they know about the exam questions, but they have this guidance, right? This senior lecturer or professor parents can advise, what subjects is better, what is easier, what is good to take, what is not. They have seen it, they have done it, they have gone through the educational route, right? So they will get, or it may not be university, it could be that these are junior college teachers who know better, right? Or whatever it is. So you get the idea that it is not a very, how do I put it, convincing calculation, and therefore your result coming from this calculation is not convincing. But to their surprise, you say, no, I did it using a PET test. Here is where you can, get back your guilt-free status of that challenge. Why? Because when you do pairing, right? When you do pairing, you are basically pairing up relevant data measures. So for example, GPA from the elder sibling paired with GPA from the younger sibling from the same family. Now, in case you think that is the logical thing to do. I'm just saying that it is also possible that you do the vertical averaging. That means you average up all the elder siblings, regardless of which family they are from, right? So it is also possible to do the unpaired test. But for paired test, you must construct this minusing at the data level. The data now is the GPA. So GPA of younger sibling minus GPA of elder sibling, that's the population point, must be greater than 0. That's the claim that the younger sibling does better, right? Then someone accuses you, hey, no, some families are richer, well-to-do, some families are not. Then you say, well, fine, because they are paired under the same family and not randomly, not randomly. And it makes no sense to pair them randomly. So when they are paired under the same family, so family 1 is row 1, family 2 is row 2, you can imagine that, right? So when you calculate that, you create a third column called D. D for family 1, D for the difference in GPA, right? Then you can see that this minus is not just calculating the difference, but it's also noise cancellation. Okay, I use the word noise in double quotation mark. You understand the word noise, right? Noise means not meaningful to us, but we don't call it noise, right? We call it confluence factor. We call it non independence influences and all that. Whatever it is, we understand that it is socially a complex issue. But if you minus off, right, sibling performances under the same family, then the noise cancellation effect takes place, which means if the family is rich, both siblings, right, tend to get more learning opportunities. And rich families, there are tiers of rich families, right? And there are rich families who don't care about spending money on education. There are rich families who spend a lot, right? So again, whatever claim you make, whatever claim the skeptics make, you can defend yourself by saying all these are cancelled out. You are saying rich family spends a lot. So the same family can reasonably be spending a lot on both siblings. Now, if you tell me, no, not necessarily, the family might want to favor the younger sibling and spend more, that part is very hard to substantiate, right? The skeptic better produce data to show that. So they better do their data collection themselves. But we can defend our argument by saying richer families, right, if they are keen on spending on education, they are likely to spend on both the siblings. So they will cancel out, right? So if they both perform better and the young one perform better because the claim is that the DNA is enhanced, right? The DNA learns from the environment after the elder sibling, the younger. Okay, so the elder sibling, right, perform, and when the younger sibling is in the fetus development stage, learns from the environment and becomes smarter, more intelligent. So they also carry through and tend to perform better in the university. So maybe there's some truth in that, and we want to show that in a more concrete way, right? Social studies and all that stuff. Maybe to encourage more births. So the first one is a test reference level. The second, third children, right, will be smarter and more intelligent. If this is true, if this is supported by. So the accusation that rich families spend more and give give one of the siblings better learning opportunities, that is going to cancel out. Right? Ultra rich families who spend even more, again, is going to cancel out. Right? Families who cannot afford to spend more than the school fees, right, also will cancel out because if the siblings are, from a very motivating family, parents urge them, tutor them, nurture them, even though there is no extra money for tuition or whatnot, right? So they both will be nurtured in the same way, right? So unless we are saying that younger siblings having seen the elder siblings, right, uh, work very hard and achieve nothing, so they tend to slacken off. Or the other way around, right? Younger siblings are encouraged by the elder siblings, that's why they work harder. That's why they tend to perform better. Whatever is the case, that is the very hypothesis we are testing, right? That means all other factors being constant, is it true that the younger sibling on average performs better than the elder siblings? That's the main reason why PET tests would be much more credible, the conclusion, right? You can, of course, eventually carry out an unpaired test. You will also get reject, non-reject, and then you will say, hey, you know what, therefore this and that. But that is going to be subjecting yourself to more accusations of this potential, that potential, right? So this minus sign is very significant at the data level. So I still like to think of it as the noise cancellation effect, because that sounds much cooler, right? Than holding all other variables constant and all. Okay, so in social studies like the one I just gave, siblings from the same family, and because that comes in very strongly, right? Everyone can understand that part, right? That performance of child in university or in high school, primary school, uh, can be good or bad due to many reasons, not just one reason, right? No single reason can explain that performance. But uh, when we are comparing populations, so the population of younger siblings and the population of older siblings, uh, pairing makes a lot of sense. Yeah. So therefore, we want to kind of maybe remind ourselves that that the rule of pairing, right? The rule is that when to pair, when to pair depends very much on there is there is um, reason, context, acceptable reasons. You can invent your own reasons, but it may not be acceptable, right? To your audience, to the general public, acceptable reasons or contexts, like from the same family, right? To associate or pair uh, one measurement with another specific measurement one measurement from population one, with another from the other population. So by way of example, I have given the being from the same family. That's the reason or context, right? That is very acceptable. That is allowing us to defend ourselves. Okay, so this doesn't have to be very invisible, very hard to find, because if the reason and the context is very hard to illustrate or convince people, then the pairing is very weak, and your explanation is likely uh, not going to be accepted by your critics anyways. For example, if I say, well, I'm doing pairing because the siblings are staying in the same HDB block. That is not wrong if you're doing, for example, um, you know, sleep disturbance at night, right? And you want to sort of cancel out the effect that some neighborhoods are quieter than others, right? So how can you do this? So, well, no, these are all staying in the same HDB block, right? That's why it will cancel out. If you say the neighborhood is noisy, then it will be equally noisy for both of them, right? But we're not doing that. So that the fact that the reason or the context that these siblings, one from family Tan and the other one from family Lim, they happen to stay in the same HDB block. That's why I pair them. That is not an acceptable reason in our study, right? So relative to our goal, that's not acceptable. So you can see that the reason and context itself or themselves need to be also very clear, very obvious in that sense once you point it out. So then it becomes noise cancelling effect. So keep that in mind when you when you are the one deciding whether to pair or unpair. If you are the one who is trying to solve it like a student, given a set of statistical data, use an appropriate two population B-stats. Okay, now you need to decide whether the question setter wants you to use paired or unpaired tests, right? Because you're going to write your hypothesis very differently. So you now go on the reverse. Just because the two pieces of numbers, one from each population, are listed on the same row doesn't mean they have to be paired, right? So you want to check, analyze the question. Is there a reason to pair them or not? Right? Typically, the question setter will put serial numbers, right, to mean that they are coming from first investigation because on that day, right, the inspection was done on company A and B. So if maybe they're selling food, right? So if that day was very hot, then it is hot for both A and B. But A didn't implement good food protection measures, no air conditioning, no dehumidifier, no whatever it is, right? Inert gas, whatnot, to preserve the food. That's why the food is poisoned and causing issues to the public. Company B did use active air conditioning, dehumidifying systems and all that stuff to protect the food very well with the integrity. That's why company B has nothing, right? No bad consequences to the public when they sell their food. Then company A says, no, but then you did different things, you check on me on hot days. Then of course our food will rot quicker and whatnot, right? Will become stale quicker and then attract bacteria. That's not fair. Then you say, no, we do a paired test, right? We are pairing these two companies together, even though you are different companies, different shareholders, different practices altogether. But we did it on the same day, right? Under the same hot conditions or the same rainy day conditions. How can you say, right? That's the cancelling effect. So that potential critics could be the population themselves, because they lost, right? Will not be able to challenge your outcome. Whether it is reject or not reject, it's not the main thing. Whether they disagree with the outcome, right? So is your outcome defensible? You need to have a good reason or context to pair, right? So make sure you inspect the question for that reason or that context. Okay. And the lack of which, if you are unable to, then something will happen. In other words, you fail to find the context and reason. That's one. Number two, the sample sizes will start to may differ. They may be still the same, but they may differ. So when you pair them, the sample size from population 1 and population 2 must be the same. If you measure the GPA of younger sibling, but the older sibling didn't tell you, forgot, didn't email you or whatnot, then you have to discard. Because if you're performing a paired test, you cannot know one piece only. Cannot. You have to get both. So the sample size for 1 and 2 will always be the same. But for unpaired tests, the sample sizes may be different. Can be the same, can also be different. So in that sense, it's more flexible. Right now. So earlier on, I was saying that if you have a medical new drug, you want to test on placebo basis, right? Whether the new drug is effective. So just because it's a new drug, it is not mass manufactured, there are limited doses, right? And you have 20 volunteering patients. You don't want to tell some of them, sorry, we don't, we still want that. But you want to you can only give 5 out of 20 patients the new drugs, so that the sample size for new drug population 5, the no drug population 15, right? And then you test, because we cannot have just the patient's reactions, whatever it is, like the number of cancer cells left in the fixed milli drops or whatever it is of blood, and count them using machines or whatnot. So it cannot be doing the measurement of the set of patients with new drug and then comparing it with certain number. Oh, if it is below, 1,000 cells per 10 droplets of blood, then it is very effective. You cannot, because it's a new drug. You don't have a standard yet, so you don't know how many cells is good enough, or is effective. You can only do a comparison with the placebo. That means patients who thought they get new drugs, but actually, no. Okay, so that you will, after the end of the trial period, you can then compare the cancer cell counts, right? And then decide whether this is effective or not. So yeah, then you have to use two population, and because the sample size at the start of the whole clinical trial, you don't know how many patients will meet the medical criteria, right? Like maybe stage 3 and above, that kind of cancer stages. Volunteering must be from this country and not beyond. Must be of certain race or certain age, just so that you can medically standardize them, statistically standardize them. You also don't know how many can qualify. When they qualify, you also don't know how many will consent to it. Huh? No money. You're not paying me money for it. Oh, then I don't want. Right? So who knows, right? There's a chance that it's not the new drug. I think I better not. Something like that, right? So people might not agree. So you would then want to prepare yourself for the unpaired test situation. And in that situation, so long as you have a conclusion, that's a very amazing thing already, right? So it's very good evidence, and people will find it difficult to accuse you. Hey, but then the patients come from different walks of life. So that's why in the selection, in the narrowing down of your population, you need to clear the medical part, clear the statistics part, clear the legal part, maybe, right? And then clear the consent part, privacy part, and whatnot. So not easy to do that. Your sample size is going to be your population size is going to be very limited in the first place, right? And then your consenting criteria meeting samples, patients, volunteering patients, will be even smaller. So that's why every volunteering qualifying patient is very important. Right? So unpaired tests will be acceptable because it's just hard to find paired, right, in that sense. Okay, then what happens is, well, we now understand, right, the difference between paired and unpaired. And what I just like to do for the paired case is to quickly uh, draw a diagram, if I may squeeze in here. Okay. So at first, there are two populations, right? X1 and X2. Okay, so there is a mean, there's a mu1, and there's another mean, there's a mu2. I draw them apart just to illustrate, right? So this could be 0.01, this could be 100,000. I'm not going to label them, but just to illustrate that there are two means, and what happens is that we are going to, so there can be some. I remember that it is going to have some sort of distribution that need not necessarily be normal, right? So it can also be like that. and I'm just trying to purposely illustrate that. Okay, roughly, you can roughly say there's a normal, they are roughly normally distributed, but it's also not very uh, nice, not very good match to normal distribution. But we were saying earlier on, in one population situation, sample size n can be made larger, right? Then we can get central limit theorem and all that stuff to deal with x bar. This one is x1, the original parent distribution. So what happens next is something I would say amazing for PET test, and that is that we construct not x bar or x1 bar, x2 bar, but we construct directly from the sampled data to get our D. Our D is the entire population itself. Entire population itself, right? Mu D, which we assert to be 0, but it can be anything, right? And this mu D is going to be constructed out of this minus this, this minus this, this minus this. You notice sometimes I point at the bottom, sometimes I point at the top, because they are made of individual repeated occurrences, correct? Yeah, so that you can see a histogram here and a histogram here. So when we randomly sample from population 1, the younger sibling, right? If the younger sibling performs high here, right, and it happens to be paired with this older sibling who is performing lower here on the elder sibling population, lower for the elder sibling population, but still higher than this particular young. So the young sibling. So this is from the same family. Same family. Yeah, okay. So when you subtract, you will end up getting one positive point. Let me see. Young minus, I did say 2 is young, right? So young minus elder sibling are still positive, right? So positive difference here, positive difference here, right? And then some positive difference here, some negative difference here, and so on. Now, assuming hypothesis is true, 0, then we ought to get more occurrences in the middle, right? Something like that. Again, I'm purposely distorting it to be not so smooth, not so normal, to highlight the fact that it is these minus these, this minus this. There's no guarantee that it'll be symmetrical, nice, smooth sailing even, right? So I'm going to get this. And from here, we will construct our D bar. This is mu D, and our sampling distribution of sample mean of the differences. So our mu D bar, which from the one population case, because now it has been reduced to one population, right? So at the individual level, data level, we construct a new population. But this minus this is this, right? And if I may just use another color, okay, so this and this, they are from the same population. So this and this gives rise to this. Okay, and this and this, right? They are from the same family. So this gives rise to this, for example, right? Like that. Right? And so you can see how this picture can be constructed. Of course, it looks more and more complicated if I highlight more and more pairs, but the idea is that that's paired minusing, right? So this population, we only obtain certain samples, the colored ones. So the colored ones will be interpreted under D bar. That means if we had repeated this n sample size pairs infinitely many times, right, then we will be able to obtain then by 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 assumption, right? That this D is normally distributed, we get a T distribution. Like this, right? So we convert it, and our T can associate with the sampling distribution. This part is 0, and this part is 0 also, right? And that's it. So this is how this is the playground we deal with. We reject or not reject based on this. So our rejection region is on the right side, right? So our alpha is going to be here, rejection region. And then we measure data and so on, right? So we can continue from there. This is just one population. Just want to show you this part, which is less intuitive, right? In one population case, we start with this right away, right? But here we want to combine, construct, then sample. In that sense. Okay, so that is our little story for PET test. What if it is not? Okay, if it is not, then we have to consider, truth be told, is that we have to consider three things: the shape or the distribution, right, of parent population 1, parent population 2, the variance of population 1, population 2, the sample size population 1, population 2. So that's yeah, quite a lot. That means, are the populations normally distributed? Do the populations have known variance or not, right? And sample size, are both populations sampled with sample sizes large or small? So 3 questions, yes, no answer, right? So altogether 8 combinations. And I haven't started talking about what if one population is normal, the other one is not, right? One population has known variance, the other one is not. I haven't started talking about those. So by right, if you want to handle all these situations, well, there are many, many branches, and that is just unnecessarily confusing. So let's just say that it's up to you. If if one parent is normal, the other one is not, you can assume. But if it's known to be not normal, then maybe we are doing the wrong thing, because you want to minus apple with apple, orange with orange, right? If one population is roughly normal, the other one ought to be. For example, you're measuring test score. If one class performance is normally distributed, the other one ought to be, right? So it might be safe to assume. You don't want to compare the quiz score of one class with the throwing of coins, Bernoulli distribution, by the students of another class. That's not a fair comparison, and you can hardly minus the test score with the count of head appearing in this calculation, right? That's not the right thing to do. So unlikely in practice to happen unless you give me a very, very almost like artificially constructed situation. Okay, so let's deal with that. So both parents not normal, then you better increase your sample size. You know why, right? Because in one population, we can then use central limit theorem. In 2 population case, same. Or same, because, as I will show you now that we understand that all the time we'll use unpaired, but when situations permit and we have, found good reasons and context, pretty obvious one, pretty easy to identify ones, pretty useful ones for us to defend our integrity of the conclusion, or whether to reject or not reject. Our defense of that is very strong, because of noise cancellation effect. So if you can find that reason or context, then try to do the PET test. PET paired tests that are done can also be done in unpaired form, but the conclusion, whether to reject or not reject, is going to be, subjected to suspicion and challenge, right? Because of the lack of noise cancellation effect. Even if you're right, that means, see, I did the paired test, it's still reject, same as unpaired, right? Even if you're right, then why aren't you presenting paired test, right? So do the paired test to give you the noise cancellation effect. In fact, I said that so many times, it's so important that I think we should note it down. Noise cancellation effect. You know those earbuds that you buy, the Bluetooth earbuds, right? Those with active, those with active noise cancellation effect sell a lot more expensively, correct? So that's why if you can do paired test, you are going to gain much more integrity, confidence in your statistical conclusion. Okay, now let's talk about unpaired test. For unpaired tests, continuing with this diagrammatic illustration, right, we will start with two populations as usual because we're trying to compare them, right? X1 and X2. And we have mu1 here and mu2 here. Again, the units can be thousands apart or micrograms apart. We won't try to label them. Okay, so at first we have this population, okay, roughly symmetrical, okay, but not necessarily perfectly symmetrical and positively, negatively skewed, zigzag. You can't say it's normal, but you can also approximate with normal, right? So we start with that. And we also have this sigma 1 and sigma 2. Okay. And what happens is that we will sample from x1 to produce x1 bar. Yeah, so we will sample and we will produce x1 bar and x2 bar. Yeah, this is much like treating the two populations twice, once as one population sampling only. We haven't done the test yet. So this is going to look a little bit more smoothened, all right, and a bit sharper, especially if the sample size is large. Okay, I'm just going to draw it this way. Okay, so that the standard deviation is going to be sigma 1 over n1. Yeah, and the other one, sigma 2 over n2. Square root of n2, sorry. Because the variance is sigma 1 over sigma 1 squared over n. So square root of n1, square root of n2. So far, so good. Okay. Now what happens is that when we perform unpaired tests, we are literally first finding the mean, finding x1 bar, little x1 bar. We take the sample 1, find its own average. Don't care about sample 2. Then we take the sample 2 and find its own average and its own standard deviation. Don't care about sample 1. So like that. And of course, that would have to be combined, right? So in this case, we would want to then combine them to come up with, so we'll combine them and come up with one so-called final sampling distribution of sample mean. So this is going to be what I will call as V bar. Okay, let's just call it V bar. And V bar is going to be much more smoother. Okay, and this would be mu of V bar right? And this would be, because it's now one population, isn't it? Yeah. Sigma of V bar. Okay. So of course, the main thing is what is V bar, right? So the V bar here is actually x1. In this case, we will do x2 bar, right? So x2 bar minus x1 bar as a random variable. That means we're subtracting sampling distribution from sampling distribution to come up with a new composite random variable. You can call it V, but I think it's more appropriate to just put a bar there. So V bar is not the sampling distribution of sample mean of V. There's no population V. I'm just using the bar to indicate that it's actually bar minus bar, right? So then the mu of V bar is the expected value E of V bar, which is E of x2 bar minus x1 bar. Right? So we can apply the linear separator to get E of x2 bar. E of x2 bar is just mu2 minus E of x1 bar, and that's just mu1. So basically, this point is what we are trying to center on, right? Mu2 minus mu1. So we assume H naught to be true. So indeed, this is equivalent to 0. Now, during hypothesis test, we assume mu2 minus mu1 is 0, remember? Yeah, so we assume this is true. True means equal to 0. So we are centering it on 0. Of course, if you assert that mu2 is better than mu1 by at least 3, then this has to be 3, then this will be centered at 3. But right now, let's just keep it simple. Right? And we also must talk about sigma V bar square. First of all, the variance, right? So the variance of V bar is the variance, I'm not going to write it out, but just verbally, right? So the variance of this whole thing, which is variance of x2 bar minus x1 bar. And assuming x2 bar is independent of x1 bar, we can split them, right? And the minus is squared. Minus 1 becomes squared, becomes plus. So essentially, it is the variance of x2 bar, the variance of x2 bar, right, which is sigma 2 squared over n2 plus the variance of x1 bar. So it's sigma 1 squared over n. So sigma V bar is going to be just taking the square root of this, yeah, and therefore sigma V bar is just the big square root of sigma 1 square over n1 plus sigma 2 square over n2, which is why I don't want to squeeze in here. It gets very hard to read. Okay, so that's the sigma part. But if we use sample, then the point estimation comes in. Sigma 1 square is algebra wise, we replace sigma 1 square with s1 square, sigma 2 square with s2 square. But statistically, we say point estimated with s1 square, sigma 2 square is point estimated with s2 square. Okay, so that's the picture that goes on, and that means we are going to operate on the V bar here, right? So our test statistic is going to be essentially a t-test statistic. So that's why you always see t-test. Although z-test is not impossible, but you will tend to see t-test because you'll gather data in practice, and data tends to be almost always because we are trying to find out the mean differences, the differences of the means, right? So since we don't know the means, all the more we wouldn't likely to know the variance. Okay, but before we move on, it is important to distinguish that in the case of unpaired test, okay, we'll be using t-test first of all. We need to check. Okay, so check what? Check. I'm just trying to decide which way is better. Okay, so maybe go downwards. Okay, so go this way. Okay, is n large or not? Okay, yes, if it is so, and if it is no, no. If n is small, then we want to ask, are we assuming equal variance? Remember that n is small, sample size is small. When I say n, you might be wondering which n am I referring to, right? Is it n1 or n2? Both. All right, so we are not going to distinguish both, like n1 small, n2 is large, right? Just treat them as the same magnitude, order of magnitude. Then we either assume or we reduce degree of freedom. Let me just write down first to emphasize lack of info or compensate for lack of information of sigma. Okay, so let me just walk through very quickly here, right? What does it mean by n large? If n is large, then okay. Okay means what? Okay means S1 and S2 are going to be good estimates of sigma 1 and sigma 2. Okay, so because both ends are large, we have no trouble. And so our test statistic is going to be combination of population 1. So we have like population 1, and we get a sample, right? The sample S1 will give rise to X1 bar, S1, and of course N1. Then we have population 2, of which we selected sample set 2, right? And this gives rise to X2 bar, S2, and N2. Remember, the sample sizes can be different, but under this branch, both N1 and N2 are large, right? Okay, now what happens? We need to have a formula that combines these into a single t number, right? That is interpretable on the V-bar diagram. So that's what's going to happen, which is going to be X1 bar. Need to draw this bar very carefully. X2 bar, okay, minus the hypothesized mean, population mean difference, which is this one, this guy here. So this guy is our mu naught. Okay. And this is to be interpreted on this V bar, right? So our V bar, better will tag with a T. and the standard deviation is this, okay? Sigma V bar. This sigma V bar doesn't have a over n, because the over n1, n2, they are inside already. So that's why you don't see the over n here. Okay, so now I want to put this big square root into nope, it will be S1 square over n1 plus S2 square over n2. Okay, so that is the big formula. Okay, so that will be a very nice smooth sailing case. It's a bit like finding the V bar. Right, so because we're going to put a point here, so anything that appears here will be a little V bar minus the hypothesized mean of differences, then take the estimated sample standard deviation for the V bar curve, right? So that's it. So it's exactly like a one population case. And this reminds me, right, just to complete the picture, there is also, of course, the t-test statistic here, which is basically the D bar, right, a result of averaging all the DIs from the samples thus computed, right, from the samples. D bar minus the hypothesized mean of the population mean of the differenced data, right? So this guy here is the mu naught over well, the S of D, right? So the sample standard deviation of the di over square root of n. Now n is clear because it will be paired, right? So it is equal to n1 is equal to n2. Because it's paired. Yeah, okay, so that part is easy to fathom. The sample standard deviation for the D column. Okay, so now back to here. This is the basic formula if everything is okay. Okay means we have no problem estimating reliably sigma 1, sigma 2. Remember, we are assuming sigma 1, sigma 2 are not known. If they are known, fine, then we just throw away S1, S2. We can put back in sigma 1, sigma 2, right, and just use Z, basically. Right? So that's fine. But that is going to be a very rare case in practice. Okay, then what happens when we have assume equivariance? If we assume equivariance, then what we want to do is to apply pooled variance, sample variance. That means merged sample variance. Use t-test. Okay, so what's the formula? The pooled variance is going to be our S square. S square is going to be recovering all the sum of squares of the first sample's variance, because the calculation is you sum up the square of differences then divide by n1 minus 1. So now we times back. Right? Same thing, we do that symmetrically for the second sample. And then we kind of divide through by the total weight. Some books will write it as n1 plus n2 minus 2. So actually it is just adding up these degree of freedom. So I'm just going to retain that flavor here. Right? So you can see that it's reasonable, right? Because if you have much more samples, like both are small. So like, but N2 is a lot larger than N1. So N1 is 5, but N2 is 12. So both are small, right? If they are small, then what's the worry? If you have 5 measurements and you're just going to use the 5 measurements to point estimate sigma 1 square using x1 square. Very worrying, right? Because double whammy, remember? At point estimation already some error there. And that S1 square itself is very low in fidelity, only 5 sample measurements. So very worrying. The other one is a lot better, but not much better also. 12, right? Sample size 12. 12 is a lot better than 5. But 12 itself, and you're just going to use that point estimation, right? So what if we assume sigma 1 square, sigma 2 square, they are the same? They are just sigma squared. Then S1 square is one attempt, right? The 5 measurements, they are one attempt to estimate sigma square. S2 square, the 12 attempts to measure or estimate sigma square, but they are just trying to aim at the same target, right? Why don't we combine our strengths in a weighted manner? So if if S2 is 12 in sample size, we listen to that more. How much more? Weighted proportion. So if they are equal in sample size, then it'll be half-half. So that's just being fair, right? What happens once we have calculated S squared? We replace in T stats formula, this one on the left, S1 square and S2 square with S squared, finish. So that's the way to deal with a small sample size case. So in small sample size, the worry is the double whammy, right? Point estimation using sample, standard deviation or variance, bad. Then the estimation themselves are bad because of low sample size. So we are going to use this strategy. Assume equal variance. Why do we have two strategies? Because sometimes equal variance is not a reasonable thing to do, or we are unable to numerically verify. And contextually, it is awkward to make that assertion. Example, a teacher teaches, the same teacher teaches class A and class B, right? The teacher wonders, class A and class B, is there any difference in their performance? That's the question. So two population mean stats, right? Maybe both classes fail their test, but is there a difference? Is there a material difference, significant difference between the two classes? Maybe one is evening class adults, working adults. One is daytime, full-time registered students. Is there any difference, right? So in that case, is it reasonable to assume equal variance? Okay, so this part is a bit like waving hand on it. You can say, yeah, they are just students, right? Or you can say, how can you assume equal variance? Because one is full-time students, one is part-time learner, right? And working adults, so more mature. So how would the variance be the same? Should be even higher in variance for the working adult class. Okay, so this is up to a teacher. It may be convincing to say, no, but they are still students. We shouldn't assume there is differences in variance. So can we assume equal variance? If we cannot, right? If it is really contextually hard to be persuasive to assume equal variance, then this way of doing it is just no way out, right? Yeah. Assuming that class is a very niche class. Okay, so like applying AI to find the best cooking recipe class or whatever it is, right? Very niche area, not many people interested. Okay, so class size 5 and 4. Okay, so the sample size is going to be very, very small. Can we assume equal variance? That means had there been a lot more students, can we assume that the population variances are the same? So that part, if it's hard to assume, very difficult to convince people, and also not many samples to substantiate any variance test, variance equality test, then we have to go by the other way, right? The other way is going to uh, reduce. So we'll keep the S1 square, S2 square, despite their low fidelity, right? They are low resolution in estimating, in point estimating sigma 1 square, sigma 2 square. We're going to live with that, but we have to still compensate for this lack of knowledge, lack of fidelity of sigma 1 and sigma 2. So the idea is thought of by these two statisticians called Welch and Satterthwaite. So we're going to use the Welch-Satterthwaite formula. So the Welch deserves their names to be written here. Satterthwaite formula. So their strategy is to keep the formula for t statistic. So keep, but change the not S1 square, S2 square. Keep everything as it is, but change as in reduce. You don't increase DF. Increase DF means, remember, DF goes to infinity, means like Z. Z means we know sigma, means we know sigma infinitely well. So DF, in this case, is going to be reduced, also penalized. They say that in this case, the DF is going to be calculated precisely using their formula that looks like this. Okay, so it's a pretty nice formula, pretty symmetrical. Doesn't matter you write S1 first or S2 first. And so S1 square over N1, this seems to be the same ratio that's being used throughout. And then you divide again by N1 minus 1. But this stacking is done up to this level, 4 levels. 1, 2, 3, 4, 5 levels. Okay, so square over, and you can guess it will be N2 minus 1. So they say, in this case, then keep everything as is. Because you cannot assume sigma 1 square and sigma 2 square are the same. You don't know their values. You cannot ascertain them because it's too expensive, laborious, time consuming to do that. And waving your hand, pulling your seniority, pulling your rank, doesn't seem to work. Fine, never mind, keep it as it is. But change the shape of the T curve, change this curve by reducing the DF, or this looks complicated, but the essence is it will reduce the KF. By how much? Well, I didn't write, but this degree of freedom here is N1 plus N2 minus 2, right? Not surprisingly, because the pooled variance also has this degree of freedom. So this degree of freedom also is N1 plus N2 minus 2. So it's like, you do know with good fidelity, but we cope with the small sample size by increasing the sample size so that our S square is 12 plus 5, which means 17 sample size estimate of that single number, the common variance, right? So if you can assume equal variance, sigma 1 square equals to sigma 2 square, right? That is, assume, apply pooled variance. So assume equal variance, i.e. sigma 1 square equals to sigma 2 square equals to sigma square. Right? So we just need to point estimate this sigma square value, that's all. So only one number, and with increased sample size of N1 plus N2, right, we ought to have a more believable story than otherwise. So that's the deal. But over here, this is going to be lesser than N1 plus N2 minus 1, definitely. So in other words, the shape of this will be bloated. Okay, so it will be fattened tail. I'm going to exaggerate it. It's going to be like that. Right, so The degree of freedom being lowered means that the tail will be a bit bloated up, uh, uh, indicating that we have less certainty over extreme values. Okay, so that's the strategy to deal with it. Okay, so that's basically the whole idea.